Okay, I think we can get started. First of all, thank you for coming. I know I am right now probably the last thing between you and a big fat cocktail party, so I appreciate you coming here. A little bit about me. My name is Taylor Getz. I'm a member of the technical staff at Hortonworks. I'm also the PMC chair of Apache Storm, an ASF member, and I'm involved in a number of different Apache projects. So a lot of the technologies that I'll be talking about today are unsurprisingly Apache projects. So Gartner's predicting that by 2020 there'll be 26 billion devices, 26 billion IoT devices. To put that in perspective, that's 5.5 times the entire IPv4 address space. So if you've watched the keynotes and watched any of the other IoT presentations, you understand how huge IoT is becoming. With sensors, phones, connected cars, wearables, even software as a sensor. And the use cases cut across virtually all industries. So today I'm going to talk about IoT architectures. I divide it into 3 tiers. The origin tier is basically what I call the origin tier is the devices and data sources, the sensors and constrained devices like cars, phones, wearables, that sort of thing. The transport tier should not be confused with like network transport. It's more about orchestrating data flow between data sources. And an important part of that is that it can be bidirectional. And I'll get into that a little bit later. And finally, there's the analytics tier. And that's where the analysis of unbounded, and when I say unbounded, I'm referring to streaming, and bounded data sources. When I say bounded, I'm talking about batch processing. And finally, acting on the insights that those analytics give you. And when you act, that's when the bidirectional component comes into play. So I'll start by looking at the origin tier. This is where data is born. But it's also a destination. So a lot of IoT use cases involve a feedback loop from the device, possibly all the way to the data center, and then back to a device or the same device where the data originated. And the origin tier is where the sensors, devices, phones produce data. This is also where constrained hubs and gateways live. And I'll talk about that more in a little bit. So devices are getting smaller, cheaper, and increasingly network enabled. And some good examples of that are Raspberry Pis. Raspberry Pi is just $35, and it's capable of running a full operating system, complete with network stack. And then another example is the ESP8266, which is a less than $5 Wi-Fi enabled microcontroller. And that allows you to wire in all sorts of sensors, and then using the IP stack on there, you can interact with Internet Protocol services. And there are a lot of other devices like this. Devices like Raspberry Pis that support a full OS are usually more used as the hub in a IoT deployment. I'll talk a little bit more about the hub and spoke model in a little bit. So devices in the origin tier both transmit and receive data. That can be used for command and control and actuators. So sending data back to the device so it can interact with the physical world, like turning a light on or closing a valve, something in the real world. And then also end user alerts and notifications. So like sending data back to your thermostat saying, do you want to turn the heat up or down, something like that. So in IoT deployments, as I mentioned earlier, you usually have the constrained devices and then a hub that connects to the cloud or to the network. And there are a number of different protocols that are involved there. So the protocols are for device to device. So one device in the house talking to another device, and then device to gateway communication. That's devices feeding data into the gateway and the gateway sending it off to the cloud. There are two basic categories of IoT protocols. There's radio frequency protocols and IP-based protocols. Radio frequency protocols are typically for very resource-constrained devices. How many people have a home security system? And how many people have one that has wireless sensors in it? So you have sensors that are communicating over a radio frequency protocol to a hub or gateway. So in that sense, the hub is akin to the main panel, your main security panel in your house. Radio frequency protocols are typically short range and low power. So when you think about those sensors in your home security system, a lot of them are very basic, like a Hall effect sensor that will detect when a door or a window is opened. And it's very small. It takes like 1 or 2 coin batteries and then uses radio frequency to talk to the main panel, the hub. The first protocol I'm going to talk about is Zigbee. Zigbee is intended for low power applications, typically applications where the manufacturer wants to be able to get up to 2 years of battery life out of the device, low data rates, and simpler and less expensive than wireless personal area networks like Bluetooth. The range for Zigbee is between 10 and 100 meters, and that's line of sight between nodes, but messages can hop because they can form a mesh network. So if there's one area of your house where one sensor can't talk to another, it can route around the failure, similar to IP routing. The data rate is low. It's about 200 kilobits per second. It supports star, tree, and mesh network topologies, and requires a coordinator device for every network, and that's usually the hub or gateway. Z-Wave is a very similar protocol that targets home automation. Again, it has low power and low data rate. Unlike Zigbee, Z-Wave is proprietary and there's a sole chip vendor. So any Z-Wave device, a single vendor made that chip. For Z-Wave, the range is about 30 meters, again, line of sight, and messages can hop so they can route around it. Data rate is a little bit smaller, 100 kilobits per second, largely because with home automation, you're mainly just turning things on and off. With Z-Wave, it forms source-routed mesh networks and, again, can route around failures. Devices must be paired. If you have any of these devices in your house, you realize you usually have to go to the hub and click a button and wait for things to be paired so that they know about one another. And it requires a primary controller, usually the hub or gateway, and has a limit of 232 devices per network. but networks can be bridged, so you can create larger networks. Bluetooth and Bluetooth Low Energy. This is pretty ubiquitous. I'm sure everyone in here has a Bluetooth device. It targeted towards wireless computer and device accessories. Compared to the other protocols I mentioned, it has high data rates. It does not form routed networks like Zigbee and Z-Wave. And it's usually one host to many device pairings. So you may have your computer with a Bluetooth mouse and maybe a Bluetooth headset. The range varies from short range of ½ a meter for class 4 devices up to 100 meters for class 1 devices. I've not seen a whole lot of class 1 devices. Usually it's in the range of ½ a meter to 20 feet, that sort of thing. And the data rate, as I mentioned earlier, is very high. So 1 megabits per second up to 24 megabits per second. Thread is a new wireless protocol that was introduced by Nest and supported by a number of other corporations. And it's built on top of the same radio specification as Zigbee. One of the more interesting things about it is it supports IPv6. And it can form mesh networks with hops supported, like Zigbee and Z-Wave. And it's very low power. They purport that it support years of operations on a single AA battery with deep sleep modes. And it is very new, so the future is unsure whether it will win out over other protocols because Wi-Fi, Bluetooth, Zigbee, and Z-Wave are already pretty ubiquitous and entrenched. So the second half of protocols is IP-based protocols. These are ones based on the Internet Protocol, so they require a full IP stack. They typically have much higher power consumption, but they have longer range, like Wi-Fi with repeaters, you can get up to a mile and further. CoAP is the Constrained Application Protocol, and it's designed to be run on microcontrollers with as little as 10K of memory. It's a simple request-response protocol, very similar to HTTP, except in this case it's based on UDP. And it supports the REST model, so get, put, post, and delete. And it has strong security via DTLS. And the way it achieves that small footprint is it replaces a lot of what in HTTP would be verbose headers with single bytes, and then supports a subset of MIME types and the HTTP response codes. It's data model agnostic, so whatever the payload, when you attach a payload, is simply a blob of data with a MIME type associated. And it's a point-to-point protocol, so it's request response. So it doesn't allow for communication broadcast, essentially. It's built on top of UDP. Above UDP is base messaging, which is a simple confirmable, non-confirmable message transfer. And then built on top of that are the REST semantics, get, put, post, delete, etc. Another one, and that's been around a whole lot longer and is probably a lot more popular, is the MQTT protocol, which stands for Message Queue Telemetry Transport. And in contrast, this is a pub-sub messaging protocol. So components in an MQTT network can subscribe to various events. It does require a broker, though brokers can be very lightweight, and you can very easily deploy an MQTT broker on a Raspberry Pi or even a lesser, more constrained device. And as I mentioned earlier, it's also a many-to-many broadcast. So there can be many publishers and many subscribers in an MQTT deployment. The message in MQTT is a simple topic plus a payload. And the payload is simply an array of bytes. And the topic is a path-like structure. So for example, here, let's say we have multiple users. There's myself, the room is my office, and it's the thermostat in the office. Then it also supports topic wildcards, both at the single level and multi-level. So what that means is this topic, if I subscribe to this topic, anything, so if ptgets represents my house, this is a wildcard. Anything, any room in my house with a thermostat would match that subscription. And then multi-level are wildcards. So in this case, that subscribing to that topic would match any device in my office. And the payload is just a bunch of bytes. So you define the schema for that. MQTT has 3 delivery guarantees. There's 0, which is at most once, 1, which is at least once, and 2, which is exactly once. And the broker handles the state for that information. One of the more interesting things of MQTT is something called the last will and testament. So what that is when you connect to an MQTT broker, you can specify a message that will be broadcast when that device goes offline. So let's say you have a sensor that comes online and registers with a broker, and then later goes offline, like the battery goes dead. Then what will happen is when the broker detects that, it will send out the last will and testament message so that other subscribers can realize that that device has gone offline and react accordingly. Security with MQTT is usually via SSL and TLS. One of the more interesting Apache projects in the IoT space is a new one incubating currently called Apache Mynewt. And what it is it's a real-time modular operating system for IoT devices. It's designed for use in devices with low power memory and low amounts of storage. Currently it supports many of the ARM Cortex-M based boards, including some of the Arduino boards. It has a hardware abstraction layer that gives you unified access to the microcontroller unit features. So if you'll be able to program multiple boards using the same language. It currently supports connectivity with Bluetooth Low Energy, and Wi-Fi, CoAP, and Thread support are on the roadmap right now. It also supports remote firmware upgrade. So with Mynewt, you can easily, with command line tools, remotely upgrade firmware. And it also has a number of command line tools for package management, pushing firmware into different boards, that sort of thing. So let's move on to the transport tier. The transport tier is about moving data from the devices to the data center. So the transport tier, I consider it connecting edge devices to and from the analytics tier, which is the data center, and to and from one another, so device-to-device communication. And also bridging protocols, and that's where the smart hubs and gateways come into play. So bridging those wireless networks like Zigbee and Z-Wave to an internet protocol so we can get that data across the internet to the data center or the cloud. And mainly, the transport tier is about collecting, transforming, and enriching data in motion. How many of you here have heard of Apache NiFi? Awesome. So I don't have that many slides available to talk about NiFi, so hopefully you were able to see some of the other presentations on NiFi, because I don't think there are any of them tomorrow. But basically, Apache NiFi is a data flow orchestration tool. It provides guaranteed delivery, data provenance, which can be important in the analytics tiers, we'll see. Back pressure with release, so if your data flow, if there are parts of your data flow that are running hot, then it can push back to the downstream components, and then when traffic slows down, it can release that. It has flow-specific quality of services, a great web UI for editing data flows. Data flows are modifiable at runtime. Actually, your data flow is sort of almost always running. And an important point with IoT is it supports bidirectional data flows. And if you look at the sheer number of connectors that what NiFi supports, just about any protocol or any system database queue, you can integrate it with Apache NiFi. And if there's something not out there, it's probably coming soon. So the basic concepts in Apache NiFi is, first piece is the flow file. That's the data that's flowing through Apache NiFi. And with that data is associated metadata, and that comes into play for data provenance later on. Then a processor. Processors are components for creating, sending, and routing, transferring, splitting, basically operating on your data. And then a connection acts as a link between different processors, and flow controllers act as the brokers exchanging the data between processors. Then a process group is a group of processors and connectors with inputs and outputs that as a group can act as another component in a NiFi data flow. And then I mentioned earlier that the NiFi has a great UI. It's a web-based UI for putting together the various components in your flow. A new part of Apache NiFi is something called Minify. This is a supplement to NiFi for constrained environments. It's more suitable for edge devices, constrained devices with a small footprint. It's designed to collect data near where it originates and then integrate it with NiFi. Currently, there's a Java-based NiFi, but they're also working on a C++ version that can be that's more suitable for microcontrollers. So like I said, that's a very quick overview for NiFi. So I'd encourage you to visit the NiFi website for more information, and also it has some of the best technical documentation I've ever seen for an open source project. So the analytics tier, now we're talking about acting on insights and generating insights. And this is where IoT data often, but not always, intersects with big data platforms and cloud computing. Depending on what your use case is, you may not need a full-blown big data deployment, so vertical scaling may suffice. So I'm sure you've seen here at Hadoop Summit how many different options there are. And there are tons, so I'm not going to attempt to define Hadoop here, so you figure out your own definition. Some of the key considerations in IoT applications, unbounded or stream data processing is often necessary. Some technologies that support that are Apache Storm, Apache Flink, and other stream processing frameworks. Then also bounded or batch data processing is also frequently necessary. A good example of that is training machine learning models. And this is where the Hadoop ecosystem starts to blow up. There's Hadoop MapReduce, Apache Flink, Apache Spark. And then finally, time series DBs are really common component in IoT use cases. So in that case, you could use Apache HBase, Apache Cassandra, then there's OpenTSDB. Some other consideration, latency is often very important, particularly when you're dealing with streaming data. And latency can add up quickly depending on the number of hops your data takes before it gets to the analytics tier. And another important piece is windowing semantics. So if you're calculating time series data, if you're doing aggregations over windows, you want to look for a platform that supports flexible windowing semantics. So when? I'm sure some of you have seen in other presentations the importance of event time in streaming analytics and IoT. So why is event time important? There's a lot of people just define two event times. There's the origin time and the processing time. A good example of that is airplane mode. So let's say you writing an application for a phone and it collects data as the user interacts with it. And then the user gets on an airplane, turns on airplane mode, and then continues to interact with your application. So your phone's probably storing that data in local storage on the phone, and then when it comes out of airplane mode, it's going to get shipped off to the analytics tier, and by that time, it could be, depending on how long the plane trip was, by the time that data gets to the analytics tier, the processing time is going to be very, very different from the event time or the origin time. So it's important to be able to, for the platform to be able to differentiate that and take into account both the processing time and the event time. Other types of event time include enrichment time. So for example, if your data flow, maybe you're using NiFi and part of that data flow is to do a lookup to enrich that data, then that data could also add a timestamp to the event. Then there are other types of time, like ingest time, when it came into a particular system, then other processing times. Maybe the time it left a device, the time it hit a hub, the time it passed through the transport tier, that sort of thing. And then finally, exit time. So let's say you have an event coming from a device, and then it results in bidirectional flow back to the device. You may get even more types of timestamps there. So things for like command and control, that sort of thing. So my advice is to choose a platform or an API that gives you the most flexibility with respect to dealing with the various event times. Next, I want to talk about future-proofing and scaling. So in a small to medium scale deployment, you're probably not big data. So an investment in large-scale distributed systems infrastructure really wouldn't make very much business sense. And if that's the case, you're not going to need it. And vertical scaling may suffice. So an example of that is, like, I may have IoT sensors in my house. I'm not sharing that data with anyone, so I could just have a Raspberry Pi that does everything I need for it. And then, of course, you could think of cases where, yes, you're sending data to the cloud, but you really only need one EC2 instance or something to deal with that. Then the second side is medium to large scale. So this is when a single server no longer cuts it. The V's are starting to pile up, variety, velocity, volume of data, and you need to make a move to a distributed architecture to scale with increasing demand. So one really promising Apache project that's currently incubating is Apache Beam. And what Apache Beam is a unified API for dealing with both bounded and unbounded data sources, so batch and streaming with one API. So there are a number of things like Spark streaming and Flink have very similar APIs for doing the same thing in batch and streaming, but they're really not completely separate. But the Beam API promises to bridge that. So with Beam, you have one API and multiple implementations. The implementations are essentially execution engines, which in Beam talk are called runners. Beam has a major focus on windowing and properly dealing with event times, which is important, as I mentioned earlier. It supports sliding windows, tumbling windows, session windows, and it also provides, at the API level, watermark capabilities for dealing with late arriving data. So it gives you everything you need to deal with that use case of the airplane mode. So what's available for runners and execution engines? Right now, Beam has a local runner that allows you to run it on a single machine. And then there are runners for Google Cloud data flow, and that's actually where Beam came from. It was the Google Data Flow API, and they open sourced that through Apache, so other streaming engines and batch engines could implement it. So right now there are runners for Google Cloud Data Flow, Flink, and Spark, and there are others underway. Currently, Apache Storm, we are working on one. I know Apache Apex is working on one, and several other projects are working on them. So some advice: choose the right runner for your current scaling and organizational needs. If you write to the Beam API, you can always swap out execution engines later as necessary. But it's really important to understand the limits of different runner implementations. They may not fully support all the capabilities of the full Beam API. So a good example of that is, so right now with the three runners I mentioned, Flink is currently the most feature complete, second to Google Cloud Data Flow. And then Spark and Spark Streaming, that runner is just implements a subset of the full Beam API. So tomorrow, for a more technical deep dive into Beam, one of the developers from Google is giving a presentation on Apache Beam. And it's a schedule change, so it's not on your printed schedules, but it's tomorrow, 4:10 p.m. in Ballroom A. So now that I've talked about some of the architectural components, there are a couple other gotchas that I want to talk about. So firmware parsers and schemas. So many IoT devices that transmit data, they transmit it simply as a small array of bytes, and that's mainly to conserve bandwidth. And the format of that data may be proprietary. So to be of any use to you, it has to be first parsed into a machine-readable format, or schema. And once parsed, you need to know that schema. So the problems with firmware versions. Deployed IoT devices may be running any number of versions, and the data formats may differ between firmware versions. So multiple parsers may be necessary to accommodate different device types and firmware versions. So the solution to this is a parser registry. So allow manufacturers to supply proprietary parsers and be able to load those at runtime. And have a parser API that includes a way to discover the schema for a particular parser. Then when data comes in, tag that data with the device type and firmware at the hub or gateway. Then when it comes into your system, whether it's in NiFi at the transport level or in the analytics tier, you look up the associated parser when the data arrives and tell the parser to parse the data into the schema. And then another part of the solution is the schema registry. So when parsers are registered, also register the associated schema. Then downstream components, like in the transport and analytics tier, can discover that schema based on that metadata, and then know how to parse or consume the data as it's flowing through. And finally, you should be wary of who owns your IoT data, because it may not be you. Beware of third-party device manufacturers, because data, as I'm sure you've heard from the keynotes, is valuable and everyone wants it. And frequently, they want exclusive access to it. So device manufacturers may hoard data. When you contract with a device manufacturer, and obviously this is only if you're dependent on a third-party device manufacturer. If you're manufacturing your own devices, then you're in the clear. But frequently manufacturers set retention policies that limit how long you can store the data. I've seen things like 3 days, sometimes it's longer. But then they say, aggregate and derivative data is okay. You can create derivative data, you can aggregate it, but then after 3 days you have to get rid of it. But then you also need to be very clear about what that definition is. That's it. Are there any questions? Okay, thank you all again for coming.